Welcome to lesson 4, example number 5, and it is asking us what is the maximum allowable compressive load, which is P. Kind of drew a diagram here, given the information that it gives us, which is the unbraced length is 18 foot. I guess I can go ahead and put this down here. So there to there is 18 foot, and that is a pin-pin connection, I believe. Yeah, pinned ends, which gives it a K equal of 1. And I hope you've read over, actually, do they have that? Where is that? It kind of will tell you, maybe it's further on, what the K is exactly. And let me take another look real quick. Yeah, okay, on page 77, if you go back, well, I guess it's forward. Yeah, forward. You'll be able to see what the K value, it gives a pretty detailed explanation of what the K is, and you could even, if you're interested in where those K values are coming from, you could actually look in a structural book and it will go through how do they get those K values. But, and of course I'll do some videos on it at a later date, but that might be a while, so if you want to do that, take a look at the steel book that you have. But it says that we have pin-pinned, which is, if you're looking at page number 77, it's the D. It is example D, I guess, which has a pin-pin connection, which you looked at. It says theoretical K value is 1, and recommended design value when ideal conditions are approximated is also 1. So we want to use 1. That's what that's the condition they're saying we're having. I kind of redrew it right here. So that's the condition we have. They told us we have A36 steel, which means we have a yield stress of 36 KSI, or 36,000 PSI. Also let us know that we have a W12 by 53, and then they gave us some of these, actually not some of, these dimensions can come from your steel book if you look at W12 by 53, but they also provided us with that information, so we'll just go ahead and use what they provided. It might be worth your time to look. Just once again, doing these tests, I'm not 100% sure, and I should look into this, what resources you're allowed to bring in. My assumption is they let you bring in a steelbook, and this is where you would find your information in the steelbook. It's typically in the front. I do not have my ASD book with me. I'm currently looking for it. I usually use my current edition, which is black, and it has LRFD and a little bit of ASD, but it's not exactly what they are suggesting you have in this study guide, which is ASD, and I have to go find it, but I don't use it every day except for this, so I do not have it at my fingertips. Anyways, my point is, it is worthwhile going and finding these numbers, and it's typically at the beginning of your steelbook. All right, we will begin solving. So we are looking for P, which is our axial load. Axial meaning compression or tension. Obviously we're going to be in compression, and since we are doing compression, this is going to be, I guess I would call it a column. I guess necessarily it doesn't have to be a column, but it could be a beam that you're just putting some compression load on. Anyways, when you're thinking about compression, you always have to think buckling. Tension, you're not going to buckle because you're pulling on it. Compression, you will have buckling issues, and the steelbook has a bunch of resources for these buckling conditions, and most of those have to deal with KL over R, which that's always where you will start, KL over R. And let's just go ahead and do KL over Rx and KL over Ry. And I haven't read through the study guide to know exactly what they say about this, but that and it looks like they do RXX, meaning it's bending about the x-axis. And I won't say 100% of the time, but the majority of the time, this RX axis or RXX axis is going to be what I like to call, and what is typically called, your strong axis. And this is your weak. And I hope that makes sense to you. If you have, for instance, this is all connected, but for simplicity, so you have a W shape right here. This is your x-axis, and this is your y-axis, and that's where they get the x-x and the y-y from. Is it's bending about this axis. So if you're going to have moment that looks like kind of like that. I hope that makes sense. And then if you're doing on the y-y axis, it's going to bend about the y-y axis, so it's going to bend like that. Meaning that in your x-x axis, this is your distance that you're going to be measuring that flange from. And on the other, in other words, when you're figuring out your radius of gyration, which I'll go ahead and define that real quick. But radius of gyration is one of those things where you can't. It's not great and easily to define. You can't just say, "Oh yeah, this is the radius of gyration." It's more memorize the darn thing, and it's actually pretty simple. But it has to do with, as you can see, it has to do with your I, which is your modulus of elasticity. I said modulus of elasticity, sorry, moment of inertia, and your A, which is your area. So, I guess what I'm trying to get at is just memorize this. I'm not going to get into it right now, what exactly this is, and try to define that, because that's just going to be confusing. So memorize it, and it's pretty much the higher the number, the bigger the I, and the lower number, the smaller the I. Pretty simple. All right, so let's go ahead and when you have a beam or a column, typically these are going to be columns. Let's say you have a column like this. Shoot, sorry about that. Let's move back down. Okay, you have a column like so. And remember, this is three-dimensional. Let's say there's a three-dimensional like this. I hope that makes sense to you. You know, this is Z, X, Y, let's say. And let's just go ahead and say it's fixed at top and bottom. So if you're going about, and remember, this is your plan section. This is kind of looking at your cross section and plan. So this is your W beam, simplified obviously by just showing it as a straight line member. And then you say, okay, well, our X axis and our Y axis are still the same, but we're just looking at it at a different angle, the elevation view, more isometric, however you want to say it. Anyways, when it bends about this XX axis, like this, that's the strong axis. That means it has more I. And you can go ahead and figure this out for yourself. This, looking at about the x-axis, it's going to have more I because you have more area. You have these two flanges that are far away from the neutral axis or the centroid. On the other hand, you don't, most of your area, when you're bending it about the y-axis, is right at the centroid. So that's not what you want. You want as much of the area away from the centroid as possible, and that's why these W flanges are so good at bending. All right, so anyways, we move on, and you could brace it, and this is how you'll end up getting to, is you'll look at it and say, oh, okay, well, if I have the higher the KL over R, the worse it's going to be. So you want the bigger R, so the weak axis is always going to control when you're buckling, and hopefully that makes sense to you. Because it's stronger this way, it's going to buckle this way. It's going to kick out that way, where it's less strong, and that should make intuitive sense. So if you're going to brace this thing, you're going to want to brace it here first. You're going to want to brace it right here, so it can't buckle about that weak axis. And then you can start looking, and you'll notice that, hey, if I half KL over R, I half my L, because that'll half your unbraced length, then you actually, even if you don't brace it about your Y axis, if you brace it about your XX axis, let's say, and that would be doing it like that. But if you did half, it would be actually about the same. You'd still, I know this is confusing and I'm trying to explain, but, and I may be going too fast. Even if you did brace this, well, let's just say this is a brace. That's how I'm representing a brace right now. But it's not braced this way, and the Y and the strong. It would, so that would be give you a half the unbraced length. You would still, that would what? Essentially it would double your R, which would still be less than KL over R for the strong axis. I hope that makes sense. I'm going to move on because I think I may have been trying to go too fast and get confusing. I'm trying to keep it as simple as I can. But anyways, you can see this right now. Let's look at KL over R, and you can just show, we'll show you that KL over R for the strong axis is going to be higher than, or lower rather, than KL over R in the weak axis. So the weak axis will control. Alright, so we have K, which we know is 1. Then we have L, which is 18 foot, and we want this to be in inches. So let's change it to inches. And then let's, R for our x-axis is 5.23 inches. And let me get rid of this. That's what R is again. One of those things I would recommend memorizing. So you have what? 18 times 12 divided by 5.23. And you get 41.3. Remember, that's your KL over R in the strong. 41.3. And then you, and this is really doesn't have any units, it's just a number. Unitless. And then K over R in 1.0. 18 foot times 12 inches divided by foot over R in the Y. Your weak axis is 2.48 inches, which is going to give you a higher KL over R. KL over R. 2.48. And I got 87.1. All right, and right now you know, hey, higher KL over R, this is going to control, which you don't even, you'll get to a point where you don't even have to control both of, or calculate both of them. But a lot of the times you're going to have different Ks for different directions. So it's pretty smart to just get into a habit of doing both. Anyways, now you have, this is controlling. Now this is the simple part. There's two ways to do it. You could either go it says enter table on page 316 of the AISC manual, which was reproduced actually on the previous page, which is 73. You go in there, you look for KL over R, and it has a KL over R of 87. You say close enough, or you can go ahead and interpolate between the two, and you say, okay, I have a FA, which is for the allowable stress of 14.56, and that's KSI. And that's your answer. Wow, that was easy. And remember, you have to make sure that that table, they should have 50 KSI and 36 KSI. This was, you look up top, it says allowable stress for compression members of 36 KSI for the yield strength. So to make sure it's 36 KSI in your book, sometimes you'll be going too fast and you'll look at 50 KSI as well. Or you can go into, it's actually it's reproduced below, and it says it's on page 319 through 3105 of the AISC manual, and you just go to your W shape. We looked, we had a W12 by 53. Go to the W12, and then you go down to 53, and you have 36 KSI steel. And you go down, and you said, okay, I have an unbraced length. It says, and you go down, and it looks like you use K in foot, which can be slightly confusing, but you have 18 foot and you go over and it says your max P equals 227. I believe that's kips. Alright, or I forgot to do up here, you have to actually multiply this times the area. And let's do that real quick. The area is 15.6, and I end up getting 227.1, and that matches up. 227, 227.1, and you're good.